Welcome to tonight's masterclass. I'm Robin Young. I'm the founder and editor of the OTW publishing platform, and I'll be your moderator for tonight's masterclass, which is going to be, I think, one of our most interesting and, in my opinion, amazing masterclasses we've had in a long time. The topic we're covering tonight, it's a little bit of a long one, but I can shorten it briefly. It's about additive manufactured implants for the spine. It's beyond surface roughness, next generation spine interbodies with, importantly, a therapeutic mechanism of action. This is part of the reason this masterclass tonight, I think, is going to be a very special one. It's a very timely subject. Of course, it was always been timely. We want the implants to be therapeutic. We want to have reliable and predictable outcomes. So our master faculty I say every time that we have an outstanding master faculty. Tonight, we have literally the father of additive manufactured spinal implants. And this is significant. Additive manufactured or 3D printed spinal implants are now almost half of all implants, and they're almost half of all implants for a very good reason, because they bring new functionality to a spinal implant. And that is Jesse Hunt, who is the founder and CEO of 4Web Medical, really the pioneering company in this whole sector. And joining us is also Dr. Andrew Sama. He is the co-chief of HSS's spine service and associate professor of orthopedic surgery at the Weill Cornell Medical College. To our audience, as you know, your Q&A is what makes this masterclass particularly special. So make frequent use of the Q&A button at the bottom of your screen. And with that, I'd like to turn this over to my good friend, the one and only, the great Mr. Jesse Hunt, who is the founder and CEO, the father of 3D printed spinal implants, also known as additive manufactured spinal implants. Jesse, I love having you here. Welcome.
Hey, thank you, Robin. I really appreciate the opportunity to come and talk to you this evening. And Dr. Sama, it's always a pleasure to see you here. We've got some exciting things happening, and that have been happening for quite a long time through advancements in additive manufacturing. I know that there are a lot of people on the call today that know who 4Web is and how this whole segment got started, but I know that there are some that also don't or are new to this. So what I'd like to do this evening is kind of follow a short agenda where we kind of introduce 4Web, kind of tell who we are and how we got to where we are today, and then really focus on kind of the historical timelines of spinal fusion implants and that the transition of technology or the evolution of technology over time. Talk specifically about the truss technology and what we found in terms of performance characteristics that are different than what we've seen in the past. And then most importantly, of course, is to really talk to Dr. Sama about the surgeon experience. Dr. Sama has probably got more experience with our technology and his utilization of the technology than anybody out there. So really interested for him to talk about what he's seen. And then we'll kind of get into the meat of the topic tonight, which is, what is a therapeutic implant? What does that actually mean? And why are we now able to say that this is a real thing, that it's tangible? So, and then we'll, of course, take questions from the audience, and we'll have a good time with it. So thanks again for inviting me, and I guess we just jump right in, right?
Yes, please.
So talking a little bit about 4Web. The name 4Web is an interesting name. The name 4Web is actually the name of a geometry that was discovered through work in topological dimension theory. And it has some very unique characteristics. High strength, lightweight. It can be used as a building block to create these high strength, lightweight web structures. And I originally started working on this utilizing the 4Web geometry to create. We were looking at military applications, core materials. How do you lighten up airplanes to save fuel cost? And the challenge that we had was there was a lot of entrenched. The industries, military industries, were very entrenched. Boeing engineers would say, "Hey, it'll be 20 years before you get something like this on an airplane, go do something else. We also had a challenge with manufacturing. This is back in 2003, 2004, and so manufacturing of these micro truss structures had there just really wasn't a way to do it. Truss structure and the technology had been around for a very long time. I mean, look at the Eiffel Tower. It's probably the world's most famous truss structure. The reason you can build that is because you can rivet and weld the struts and nodes together at scale. But when you start bringing 285 struts inside something the size of a silver dollar, you can't rivet and weld those struts and nodes together. And so through a lot of frustration and not getting anywhere in the military industry and different areas, I started to think through how I could apply my knowledge or this technology into what I know, which was orthopedics or med tech area. And I remember the moment that it happened. I was like sitting in my car saying, wow, how do I apply this to what I know? Oh my gosh, we've got this open architecture, the bone could grow through, fluid flow. Oh, this strong light. This could be a really interesting concept. Um, Still did not have a manufacturing capability, though, which was the gating factor. And in July of 2007, as I'm sitting there scratching my head trying to figure this out, I'm sitting there thinking to myself, if I could just figure out how to manufacture this thing, man, this would be amazing. How am I going to manufacture this? And I look down and there's a advertisement in a magazine and it has a picture of a spine cage with like a diamond cut out, which the four web geometry kind of looks like a diamond, and it's literally saying print fully fused titanium implants. Call this number, guy. And so the answer literally, just appeared before my eyes. And so that was when medical modeling, Andy Christensen had, I think, one of the first electron beam melting printers in the country. I called the number and said, "Hey, I've got this idea. Can you guys print some samples?" And he said, "Yeah, sure. Send me over a file." We printed some test samples to validate whether the manufacturing technology would actually give us the performance characteristics that we were looking for. And they did. I got so excited, I quit my job 3 weeks later and, was off to the races. And unfortunately, I realized that I needed a job to fund my venture. So I had to go find employment somewhere else along the way. But the fun part of this was that it was new and it was exciting. Nobody had ever really used additive manufacturing for orthopedic implants. There were some ups and downs along the way. I think the bittersweet part of developing something or being first to market is the time that it takes and the investment it takes to get it through what is a necessary regulatory process, right? The FDA does a great job of making sure that the patients in the United States stay safe. And the bitter part is that it takes a lot of time and money. And they wanted a lot of testing. I always said we did kind of a PMA minus the human clinical trial. We had to qualify the manufacturing technology, structural characterization, biocompatibility, fusion testing, you name it, we ran the gauntlet. It took us 3 years to get the 510(k) on what is typically a 90-day process. The sweet part of that was all of the tests that they required us to do gave us the science to actually go take to the market. We weren't just selling a cool little widget that had a bunch of struts in it. We now had something that had some performance characteristics that were unique compared to predicate devices. And what really set us off, or what really allowed us to identify that something special was going on, was when we did the animal fusion study. Uh, I call this the penicillin of orthopedic implants moment. When I was doing the animal fusion study, I was really trying to qualify two different types of manufacturing technologies. And so the DMLS technology, direct metal laser sintering technology, could go down to 0.5 millimeter diameter struts. The electron beam melting technology at the time could only do 1.5 millimeter diameter struts. So I had a side-by-side comparison just trying to get the manufacturing technology qualified, right? That yes, we use this. And the results that we got from the fusion study showed a dramatic difference in the quality of bone and the rate of fusion between the 0.75 millimeter strut design and the 1.5 millimeter strut design. I mean, it makes sense. The smaller diameter strut is less stiff, it load shares better. And what we saw is it had a direct impact on the quality and the rate of fusion. And so for the first time, we were like, aha, you mean that we can actually control the quality and rate of fusion based on structural design? And that was really the moment where you realize that what additive manufacturing provides is an opportunity to create implants with advanced structural designs that can interact with the body. So, for 4Web, look, we are a developer. Our proprietary technology is the truss implant technology. And we've been doing this longer than anybody. I do believe that we've probably got the world's leading team of developers based on additive manufacturing technology. We started in the spine area, and we have a foot and ankle business unit. We do a lot of custom implants. We provide custom implant services for tumor trauma patients that really don't have any other options. We do a lot of limb salvage procedures, which we're really proud of. And so it's been an exciting ride, and we're happy to be here. I'll just to kind of get everybody up to speed on how the technology works, and focus on kind of the topic of today, which is the spine implant and therapeutic implants. We knew how it worked, and we needed just to be able to describe or take that to market in a way that it would be accepted. And so when we looked at the legacy manufacturing technologies, like machining and cast molding, the technology has really limited the sophistication of the designs, right? I mean, look, you go back to the allograft wedges. It's just a piece of bone with a hole cut out of the middle of the central fusion column, right? You got the titanium cylinders, right? The BAKs from back in the day that still have this hole through the middle, which is the central fusion column. And then, of course, the guys in Envibio came out with Peak, which was supposed to solve the subsidence issue. It was a brilliant marketing. I love it. The reality is, was it really titanium that was causing the subsidence, or was it the design? Well, think about it. If you're screwing in an implant and your threads are cutting the end plate, which is your support structure, what do you think is going to happen? Well, it's going to collapse. So while the Peak guys had a great marketing angle to say let's go out with this modulus elasticity concept, was it really the modulus elasticity that caused that solved a subsidence problem, or did it just get us away from bad implant designs to start with, which were these threaded cages that destroyed the support structure? Moving forward, you started to see the trabecular metals, right? Which, imaging was always an issue. You couldn't see what was going on if there were problems. The only time that, or at least a lot of the times, the reason that a patient would get a CT scan post-op is if there is an issue and you need to be able to see what's going on, right? And so if you've got all this metal and an artifact, and that's not really going to be a problem. And then I think for us, one of the most interesting, probably one of the most important things that took place was how do you guide an industry along or what are the stepping stones of evolution that the industry has to take in order to be able to understand this broader concept of mechanobiology, or this how you can really communicate with the surrounding biology. And so I think it was 97 or a little bit before Titan Spine came to market. This was the first time that an implant was being modified or treated in order to have a bioactive influence, right? We're causing a roughness in order to trigger a response, initiate a response, right? And that was important because nothing before had that bioactive component. All of the previous designs were annular cages that were static spacers. That's it. The only job they had was to hold bone apart and let the body try to figure out what to do on its own. This piece of plastic with a hole through the middle of it serves the same purpose as stopping my kitchen table from wobbling. I just stick it under the leg, and that's it. It has no contribution to the healing process or the fusion process over time. So getting the industry to acknowledge, hey, we actually can do some things here to trigger or initiate a biologic response was really, really important. in the evolution or the understanding of implant technology. And then, again, for us, the advances in additive manufacturing really allowed us to create these implants with advanced structural designs that are kinetic rather than static, right? They under load, they behave a very specific way, and we're at a moment in time which I really think is a paradigm shift in implant technology, where we can program the implant in order to behave a very specific way under load that communicates with the surrounding biology and drives the biology to respond in a positive fashion, right? I mean, think about that. Static spacer just sitting there versus an implant that actually has an active dialogue with the surrounding biology to contribute or drive a process over time. To me, that is just a really exciting moment. And the way that we do that is with three primary features, right? One is the surface roughness. Surface roughness does work. Rough titanium is better than smooth titanium. This has been known for a very, very long time. And it initiates cell differentiation and gene expression. It allows for initial fixation, but it's a passive feature. Once it's done with that initiation, it just sits there. It doesn't really contribute anymore. The second component for us is the truss technology, and this is really where we are different than any other technology, and how that truss technology works in order to communicate with the biology. And then the third component is, the mechanobiology at work, right? What is the biologic response? You're saying you're doing all these things. Well, how does the biology respond to that? So moving from static spacers to kinetic spacers is where we are today. And I'll go through all three of those as it relates to the four web technology. Yes, we have surface roughness. We have a hierarchical surface roughness that spans from the macro to nano scale. We have several studies that have proven that that the cell or the gene expression is initiated. For us, there's a particular feature where if you look at the annular cages with surface features, because of the struts and the architecture, we actually have 3 times more surface area for cell attachment and for this initiation, because we've got 360 degrees around every strut throughout the entire construct, right? So just there, if you like surface roughness, I got more than anybody. But it doesn't just stop there. Where it gets exciting for us is when we look at the truss technology itself. And look, let's look at nature. You want to talk about biomimic. Bone, nature's ultimate biomaterial, is actually a truss design. When you look at it under a microscope, you can see the triangular filaments. This is what gives it its high strength, lightweight structure. And so, our implant or our design is very biomimic in nature, right? It behaves similarly to the way bone behaves in its natural state. This center portion here is what I like to call the mechanical engineering explanation of Wolff's Law. I know there's a lot of words there, so bear with me. But really what this does is it's a load curve, right? And then shows that underloaded bone atrophies. We see that all the time with big, thick metal implants that are stress shielding and bone pulls away because it's not receiving load. Then you have this adapted state. So if you can actually get a certain amount of load onto the bone, it triggers a response. I need help down here, right? Up to overload and then fracture, right? We know that the classic range for bone formation through mechanostat theory, Harold Frost's mechanostat theory back in the 70s, was between 1,000 to 1,500 microstrain. So can you design an implant that under load delivers 1,000 to 1,500 microstrain? I think there are more recent papers and studies out there showing that the range is actually about 400 microstrain and above. So, really what you're talking about is you're looking at the advanced structural designs as how do you program that implant to get as many of those struts in that therapeutic range as possible, right? And look, ultimately, this is Wolff's Law. Wolff's Law boils down to really 2 primary concepts. Wolff's Law basically says that bone will remodel based upon the environment with which it sees. If you're a couch potato, you're going to lose bone density because it's not metabolically efficient for the bone to maintain itself at a higher level. And if you work out with weights, the bone's going to remodel and get stronger because it needs to be that strong to exist in that environment. But Wolff's Law really boils down to 2 primary concepts: that bone will grow in tension Think about the Elizaroth, right? Or the bone transport systems. You're pulling bone and tissue, and it remodels in compression. Tension and compression, those are the loads or the forces that bones responds to. So when we look at these triangular truss designs, or the core component of 4Web's technology, every strut under load either holds tension or compression. That's the way truss structures work. So when somebody is walking down the street, every step that person takes, every strut in this implant is going tension, compression, tension, compression, tension, compression, tension, compression over time. It's ultimately a bone stimulator that will continue to stimulate bone until the bone overtakes the implant as being the primary support structure or load structure, and then the implant turns off. It's kind of a planned obsolescence without intent, right? And so this is, look, for us, we're really excited. In our industry, we know of three ways to grow bone. Chemical, we're going to dope it, and we're going to get something to kick off. Electro or magnetic, right? Bone stimulators, we're going to pulse, and then mechanical, Wolff's Law. This is the first and only time that we've been able to take advantage of Wolff's Law, deliver strain to the surgical site in order to drive the fusion process over time. So that is kind of our background and our story and how the technology works.
Yeah,
So
see, it's an amazing story.
yeah,
This is just phenomenal stuff. And
well,
you have talked about this several times. You cannot talk about it enough. I'm
yeah.
serious.
Well, I
Because
appreciate it. You know,
these are
when I
great
give these,
concepts.
yeah, no, I appreciate it. When I tell this story, most surgeons they say they're like, "Oh my gosh, this makes so much sense from an engineering standpoint." Wow, that's great. Hey, can you prove it? That's the big question that we've got. And look, that ultimately is, well, why we're here today, right? And is to talk to Dr. Sama. The best evidence that we could ever have is
Mhm.
surgeon
Mhm.
experience, right? What are they
Yep.
seeing in their clinical practice? And then we are proud to say that we've got a new study out of UPenn that's hot off the press that's going to take us a step further and really address this concept of therapeutic implant. So we're really happy to be here and
So,
appreciate the invite.
okay. So should we move on to Dr. Sama then?
Yes.
Talk about his experience. Okay, Dr. Sama.
Great. Thanks, Robin. Thanks, Jesse, for the invitation to be here. This is really something I'm excited about because I've been a user of 4Web implants probably since the beginning. I'm a spine surgeon, orthopedic spine surgeon in New York City. So Wolff's Law is something they kind of drill into us as we're residents and fellows. And then, in spine, we never really thought about it too much. But when you're talking about long bones and fracture repair, we think about it all the time. And it never really made sense to me as to why we didn't apply some of those same principles in spine in design specifically. So we know that, posterior spine fusion is not a favorable bone growth scenario most of the time, and bone tends to do better in the spine in compression. So that's where the interbody space becomes really our main focus when we think about getting and achieving a fusion. And we've done that in a bunch of ways. We've done it from a posterior approach, an anterior approach, an anterior and posterior approach, a lateral approach, oblique approach. So we've really kind of skinned that cat as many ways as we can skin it. But really, the fundamental issues were how do you get the bones to unite, understanding that you can access from all these different ways. And I started off, as a macro surgeon. Everybody now is MIS, and we think about sort of really sexy and elegant ways to get to the spine. But really, fundamentally, you need to decompress the neural elements, you need to realign the spine, and you need to stabilize it when necessary. And once it's stabilized, if you're not able to achieve fusion, I think you're doomed to fail. So if the bone is weak, the bone will break. If the screws are stronger than the bone, the screws will come loose in the bone, and then you're faced with bone loss and some challenging revision types of needs. When I first started out, we didn't have a whole lot of options in terms of how to stabilize or implant into the anterior interbody space. We really started off with, like Jesse was talking about, just basically allograft wedges. And one of the challenges about allograft wedges when I was starting out was they often broke or they weren't favorable in terms of the amount of lordosis that you created. Um, or if there was a delayed union, the bone would just disintegrate and reabsorb. So you were left with a big void. Those were really challenging scenarios, especially if you had to go back and revise those from an anterior approach. Oftentimes there was inflammatory rinds that grew and, very challenging spaces to dissect around the vessels and et cetera from the front. So what I was taught and believe to this day is that your first try should be your best opportunity to get a fusion and recreate your alignment and stabilize the spine. We were really never had a good way of doing that, I think, in the interbody space. And I kind of said, like I just said, rather, I started with allograft wedges, and then we went to Peak, and then from Peak we went back to some of the mesh titanium stuff that was out there. One of the things that was never really considered was two things. One was some of these implants were too rigid and more rigid than some of the bone, so they could actually act as stress risers, and we were seeing adjacent fractures. So wherever the implant was, it would fracture the bone adjacent to it. Or the other thing that was happening was the way these implants were being designed, they often had large graft chambers, and they acted like cookie cutters almost between the bone above and the bone below. So you'd see a significant amount of subsidence. Even if you performed really good carpentry at the time of end plate preparation, there was more likely to be a subsidence. And those things were very upsetting because you could do a great operation, it could look good on your initial films, and the patient comes in for their 6-week follow-up, and everything that you had achieved has gone by the wayside because the bones had collapsed around the implants. So when I first met Jesse many moons ago, and I forget where we were, Jesse, but you showed me the implant, I was like, huh, this is never going to work because there's no graft chamber. So I was sort of indoctrinated into this mentality. And he's like, no, dummy, look at it. There's so much space there. You have so much room for bone. You're going to love this thing. And I was like, all right, let me give it a shot. So at the time, all we had was the ALIF, I think, back then, Jesse. So I did an ALIF and I was like, all right, well, yeah, it's just like any other ALIF cage. And what I realized very quickly was two things. Number one, the surface topography is very grippy. I don't know if anybody ever uses that word for you, Jesse, but we use it all the time in our ORs because it is grippy. And what I mean by that is when you place it into the intervertebral space, the surface topography, the roughness actually grabs the end plates of the bones without really being too harsh. So I love that because as I put it in, I could really get a good tactile feel that as I was inserting it, I could almost tell when it was in the right depth because it just wouldn't move anymore. I couldn't really pull it out very easily. I could get it out if I needed to, but it would stay where we put it, so it was grippy. And I was like, oh, that's kind of cool. Let's see if it heals. And lo and behold, it healed. And I've used these implants since the inception with every possible biologic, autograft, allograft, DBMs, fibers, putties, you name it, BMP, we've used it all. And really, they perform phenomenally well. The implant performs phenomenally well, regardless of what type of biologic we place in it. Oftentimes, if I'm operating on a teenager, and especially a female, I don't necessarily want to use BMP. I just use either autograft or allograft with those. And lo and behold, massive amounts of fusion. As my practice evolved, and in 2005, 2006, I started doing lateral surgeries. It really revolutionized my ability to take care of elderly patients with deformities because we could take advantage of the apophyseal ring to apophyseal ring sort of strength and try to put a cage across. Having said that, that was the good news. Having said that, the bad news was we were right back to where we had started because the cage technology at that point was very rudimentary, and we were going back into either PEEK or carbon fiber or monoblock type of cages with giant holes cut in the middle of them. And even though you were spanning apophyseal ring to apophyseal ring, you would see these subsidences. So I was really excited about eight years ago now, or 7 or 8 years ago, I guess it was, Jesse, that you guys came out with the lateral truss system, and I started using it. And really, I've almost used that exclusively since its inception because of a couple of things. Number one, it does work. I mean, it fuses the bone fuses around it, through it, onto it, you name it, it's there, and it becomes very, very apparent almost very quickly. I mean, anecdotally, I don't have a study to prove this, but anecdotally, in my experience, usually by the 12-week mark, you could actually see pretty good sentinel bone in front of it. And if you were to have to get a CAT scan for one reason or another, I typically don't, but you would see bone growing through the truss architecture and attaching bone to bone. So that was like really, really revolutionary for me because I was like, holy smoke, this thing not only does it not subside often, but it actually works to help the fusion happen regardless of what kind of biologic or autograph I put in there. So that was really, really cool. And then as the cages evolved over time, We have 0 degree, we have 8 degree, 12 degree, whatever the degree of lordosis that you have, you could actually kind of dial that in and help realign your spine and recreate your alignment that you're trying to achieve. So that was very, very cool. And then all of a sudden they come out, and they have plate technology that comes along with it. So they really run the gamut and really try to solve for any of the needs that the surgeon and the patient may have at the time of care. So that's really been my story with it. When I heard this UPenn study was coming out, I was like, maybe this is something that's going to explain what I think I've known anecdotally all the time. So I'm really interested to hear, Jesse, what the study showed and basically where this takes us into the future, because I find this extraordinarily exciting.
I say thank you. I really appreciate it. It's the comments on the subsidence are good to hear. When you started with the peak implants going across from a lateral standpoint, you're on the posterior ring, but because bone doesn't attach to peak, the bone will actually atrophy around
Yeah.
peak, right? Because it's sliding, so the bone's pulling back in order to try to lock down that movement. And
Mm.
with four-web, yes, we go with pause but it's that snowshoe interface,
Yep.
right? Everybody knows how a snowshoe works, right? You distribute load over a large area so you don't sink into the snow. Well, when we can distribute load across an entire vertebral end plate, it really does resist the subsidence.
The other thing I would
Well,
mention, sorry to interrupt, but is I
mhm.
like I like sort of the convexity and the way that this sort of nestles into the native disc space. Now, sometimes the disc space is really flat in degenerated disc. Sometimes it's misshapen because there's been a discitis. But the fact that there's actually some give to the implant sort of allows you to introduce it, and it kind of finds its spot almost. It's kind of an interesting occurrence, but it's tactile. You can actually feel it. And then obviously when you see it on your fluoroscope or however you're putting it in, you can dial into where you want to put it and how deep you want to place it, whether you want to put it more anterior, more posterior. And you have your two, for the laterals, you have your two widths front to back. You have your 18s and your 22s, and that gives a lot of variability that you can build into the construct, which is great.
Yeah,
Sounds like that gives you a lot of confidence. Because again, the tactile feeling and all the rest of it.
Absolutely.
Uh, I know, Jesse, in OTW, we've written as information has come out, and you've really spent a lot of resources and other things getting really solid clinical information and now study information. And I know as it's come out of the company, we've written about that in OTW. So I am really interested to hear what is the latest
yeah.
on the UPenn work that you've been funding now for some time.
Yeah. No, we are excited about the information coming out as well. We've been working with them for many, many years pre-COVID to really qualify and quantify how the implant technology works and what the impact is. And so a lot of that is developing test methodologies, controlling those methodologies, and then getting to a point where say we're confident with the information that we're getting. So, I'd love to jump back in here and show you guys some
Hmm.
information about
Hmm.
that study. So the study was, we, of course, drinking our own Kool-Aid, thought the study was phenomenal and that the output was phenomenal. But it appears that we're not the only ones. We actually submitted the study from UPenn. Dr. Malk and Sue Chin were the ones who led that research at McKay Orthopedic, Research Laboratory. And the study was accepted by Advanced Healthcare Materials, and not only accepted, it was featured. So we got the cover. And they thought that this was such a transitional moment for implant technology that it warranted special attention, and we couldn't agree more. So thank you to the people at Advanced Healthcare Materials. But really, what the question is, what is the therapeutic implant, and then kind of what is the evidence you have, right, that shows that you've got this effect? And so, it is important. There are no implants out there that can claim to be therapeutic until now. There's a lot of people that claim nanotechnology and surface and whatnot, but to actually be therapeutic is quite special. And so we went and we looked through the FDA guidance documents and at different definitions to see what they consider what was required to be therapeutic. And first, of course, is, let's say there's an implant and the implant is well defined, four web qualifies as an implant. We've used the truss technology successfully in a wide range of orthopedic applications throughout the entire body since 2012. Check that box. All right. And I think the most interesting component about when you start talking about therapeutic is the FDA's reliance on a mode of action, right? And the mode of action is or the implant or whatever it is must contain a mode of action, which is the means by which the device achieves its intended therapeutic effect, right? So it's the cause and effect. What is the cause and effect, right? And the interesting thing about our technology that we're now able to show through the HUPIN study is that the structural mechanics of the truss architecture, its mode of action is that it converts physiologic load into therapeutic strain at the surgical site, which amplifies osteogenic activity in the local osteobiologic material. So that mode of action, the conversion of load into strain, causes amplified osteogenic activity, which drives or supports the fusion process over time. We get to check that box. And the therapeutic effect is what is the beneficial change that's produced by the product or that contributes to the healing over time. So we say over time because, we talk about surface roughness alone. Well, surface roughness is kind of a passive feature. It doesn't really have a mode of action. It sits there, bone attaches to it, it'll initiate a process, but then it's done. With the truss technology, because of the way that it's designed, every step that a patient takes is converting that load into therapeutic strain at the surgical site. And as we said, it's doing that over time until the bone becomes the primary support structure. And so that is really what it takes to be a therapeutic implant. And we believe that we're the only technology out there that qualifies as therapeutic. We like to say that the truss technology is therapeutic by design now. So,
Well, what I like about this, it's very specific. Your clarity is excellent, and it's not a marketing hook or pitch. You
mm,
have very clear, defined elements that
yeah,
add up to a therapeutic effect, and underlying it all is what you talked about earlier, Jesse, Wolff's Law.
that's right.
I
That's
mean,
right.
this is terrific stuff.
No,
Uh,
I
sorry,
appreciate.
I jumped in. Go ahead,
No, no, that
Dr.
I look
Sama.
more. Give me more, Robin. Come on.
Well, the other thing I forgot to mention too, just
Yeah.
from a surgical standpoint, is when you think about a graft, I mean, sorry, when you think about an implant that has a graft chamber, that's a defined amount of bone that goes in there. But when you think about this, the amount of graft that you can pack into this is at least double what you would pack into
Hmm.
something with a central graft chamber. So if you're using a DBM putty or something like that, be prepared because this thing will house a lot of it, and the way you pack it is retaining. It retains whatever you pack into it too, which is another feature that I don't think anybody's ever talked about, but I know anecdotally, when I use it, I'm just like, oh my gosh, this thing is amazing. You just pack it, it keeps the stuff in there, and you can put a lot of stuff in there. So not only are you getting the stress, but you also have an opportunity to optimize the biology as well.
Yeah,
Well, it's funny you say
I
that.
like to.
Yeah.
I like. Sorry, I like to.
Go ahead, Jesse. Yeah.
The knowing that bone grows throughout the entire construct, that there is no impedance for bone growth. I think Dr. Tom is a really important point to bring up. And when you have large annular rings in a small fusion column, you're just trying to get fusion through that one little dowel, right? Or that one little area. And the truss technology really is like rebar and concrete. The concrete flows throughout the rebar holds it together. Well, we're just providing a scaffold for bone to grow throughout the entire construct. There's no zero impedance of bone from end plate to end plate through this implant.
That's just amazing. Yeah, by the way, guys, the only reason I was interrupting, as we are talking, we're generating some Q&A from the audience.
Yep.
And Dr. Samas, you were just talking about you put in the DBM or whatever bone void fill you wanted to use. We did actually get a question here about biologics. As this therapeutic effect is going on, does that alter which biologics you choose? I mean, does that pull you away a little bit from some of the expensive BMPs and more towards, I don't know, other forms of bone void fill, Dr. Sama?
Yeah, I mean, absolutely. I think, if you're First and foremost, I'll take a step back. First and foremost, I
Yeah.
think the carpentry is important, right? Good end plate preparation, evacuation, nuclear material. I think that there's no implant or biologist going to make up for bad carpentry. So the onus is on the surgeon to do a good job in preparing the disc space, releasing the annulus. If you need some improvement. I think what happens with interbody, especially lateral interbody, is the surgeons get a little bit greedy. They say, oh, uh, I could put a 14 or 16 millimeter tall implant in there, but really the native disc adjacent to this is 10. So don't get greedy and try to open this thing up like crazy because you will break the end plates, even in somebody who's got strong implants. So I do believe that good surgical technique, good carpentry, so to speak, is of paramount importance. If once that's done and that's constant across the board, then you think about, okay, now I need to get this to fuse. And historically, we've depended on autograft, and then we've kind of shifted to some allografts, and then we shifted to some of the synthetics, and then ultimately, BMP over the last 20, 25 years has really taken place. And then BMP is not without sin. Our group has published some papers about neuritis and radiculitis due to the chemical inflammation associated with BMP, and that's real. So if you can minimize the dose or obviate the need for something that's expensive and potentially inflammatory like BMP, I think that's a good thing. If you have a therapeutic implant, in theory, I mean, this is blasphemous to think like this, but you may not need anything, right? Hypothetically, in a perfect world, but you want to cover your bases. You want to hedge the bet a little bit. So I would typically use, if I was going to use BMP, I would use much less than I would in any other type of cage. If I wasn't going to use BMP, I'd be much more confident, even with a synthetic or a DBM in something like this, because I think you have the therapeutic effect of the implant plus the biology of whatever you're putting in there. So I think you can use something that's less costly and less inflammatory than a BMP.
And Rob, I think there's a good,
Yeah.
there's a really good segue into the actual study, outputs
Yeah.
itself.
Let's do it. Yeah.
Because, we're talking about, what do you need to ha in order to create this therapeutic environment? And, what really what you end up with is, as long as you've got osteobiologic material or cells, or whether it's from bone marrow aspirate or you're trying to get this clot, right? This hematoma to start this process. Well, once those cells are in this cage, the cage kind of takes over, right? And does its thing. And that's what we really showed with this study.
Yeah.
What I'm going to do is I'm going to bring this up. And, what we did is we came up with a test protocol to be able to measure the impact of strain in attached cells as compared to cells that were on a static truss element. So you have a static truss element, and then you have one that's being loaded, and what's the difference in the gene expression? We use this next generation sequencing ultimately to look at that gene expression. So here you can see we were
Oh,
going back
goodness.
to this concept of delivering therapeutic strain. We had a strut element or a truss element or a strut where we seeded with stem cells. And then you put that strut under 3-point bending to cause tension on one side. The results that we got were absolutely phenomenal. I mean, first and foremost, when we looked at the smooth titanium versus rough titanium, does the roughness actually work? We did it in basal media, and then we had it in osteogenic media. And what we showed is that in the basal media, the 4-web surface roughness had a 31% increase in Run2X or Run-X2 compared to the smooth titanium. That's a basal media, right? When you actually added osteogenic media to that, you only got a 32% increase over the smooth
Now,
surface.
Jesse, I'm going to interrupt you on this one. What
Yeah.
does that mean to you?
So
32% when you're in
I think
the
it means that
osteogenic
it's the
medium. What does it
implant,
mean?
not the osteogenic media, right, Jesse? Is that what I'm saying?
that's right. That's right. If you're doing
Wow.
1% and you're not doing it through the media,
Wow.
it's the roughness itself that is causing the
Yeah.
response, not the type of media that it's in. So that
That's
that for us
terrific.
was like, okay, here we go, right?
That's
We know
really
that
interesting.
Wow.
That's pretty cool.
yeah. And then what we wanted to do is look at what happens on the rough versus static versus dynamic. So think about the gold standard implants out there that are annular and they have surface modification technology, but they're static, like we had discussed. If we now bring this and we put it into a dynamic environment, is there an impact? And what we showed is that It has significant difference. We showed up to a 30% increase in osteogenic, angiogenic, and myogenic activity based on the delivery of strain to those cells over the static surface roughness alone. So now you're sitting here talking about, wow, now I see what that therapeutic effect is doing, right? And I will take this moment and I'm going to bring it full circle to what Dr. Samo was saying about what materials we would put in there. But the real world evidence that comes out of this. We actually had a case. This is one of our custom cases where there's a 15 centimeter defect in the distal tibia due to uniosarcoma. The surgeon had asked the patient, said, look, when you pass away, don't everybody passes away. When you do, can we look at this implant for medical research? And the patient had agreed. The patient expired 2 years post-op, not for anything. It was for different reasons, but they went in and they took the implant out. Showed full incorporation of bone across the 15 centimeter defect. Not only that, in the axial view around the nail, all these little dots are the actual struts through the cross section. Histology showing new bone formation at center mass. So I do have to say that never in the history of orthopedics has anybody been able to regenerate or regrow bone across a 15 centimeter defect like this. And we can. And I always like say to my spine surgeons, if I can grow it across 15 centimeters in the distal tibia, I promise you I can grow it across 12 millimeters in the lumbar spine.
Now you're just showing off.
Yeah, I know. But the point
Yeah,
being is that we have this real world evidence of this therapeutic effect. And
Sure.
to Dr. Thomas' point on what can you use, as long as we get the cells in there, the implant is the conduit for healing over time rather than just initiating a process.
Jesse, it'd be interesting to see exactly what they put in the space or the cage, and then also if there was any adjuvant or neoadjuvant radiation or chemotherapy too, because if you can heal in that environment, I
Mhm.
mean, this is a hostile environment to begin with, but if you throw into some of those cytotoxic treatments and you grow bone like this, that's insanely successful. That's amazing. Kudos. That's really cool.
Yeah, a lot of the tumor patients that we treat, they've got the chemo up front, and then you've got like a 2 to 3 week window,
Yep.
right? We're going to do the resection before then they go to radiation. So a lot of our planning hits that time period that we go
Wow.
in and replace those big defects. So,
very cool.
That's awesome.
All right, Jesse, I am going to go through a couple of questions that came through here. I think we already covered this, but I'm going to give you the question anyway, in case you or Dr. Sama have a little more color you want to add. The question had to do with clinical evidence. They basically want to know what clinical evidence does 4Web have that demonstrates, provides some kind of evidence of the benefits of this technology compared to other interbody implants. So again, I understand we just went through evidence, but maybe you have a little more color, you or Dr. Sama, you want to add to that.
yeah, look, I think it speaks for itself, right? We talked about, I mean, most
Mhm.
importantly, Dr. Sama has had success. You can't get any more real than that. With the sheep study that was published in Spine, showing this accelerated healing, that was one component. We've got real world evidence of showing full incorporation across a 15 centimeter defect. We've got the UPenn study. All that leads up to is a nice body of work that shows that this truss implant technology is pretty special. And based on what we know now, it's going to lead to some future clinical studies that we may get into here in the near future.
Yeah, don't stop that. Keep going with the studies. I'm just saying. The other one, I think this must come from someone who's that is just sort of struggling with figuring out. He asks or she asks, wouldn't other 3D printed implants provide the same results
Mhm.
as the four web trust design?
Yeah,
Jesse?
okay. This is I get to have fun with this one if you're okay with that, Dr. Summer.
Yeah, please.
Yeah, one of the biggest frustrations that we have experienced is kind of the diluting of the term 3D printed implant, right? Or it dilutes what the actual science is. It's kind of lazy rhetoric, right? You hear people out there saying, "Hey, here's my 3D printed implant, and here's my 3D printed implant." Well, 3D printing is just a method of manufacturing. It's just, if I was to say, here's my CNC implant, it's the same thing as a 3D printed implant, right? And it really has to do with the structural design, the architecture, what you're doing with that. How do you design the implant to behave a very specific way? So, does do other 3D printed implants have the same benefit? Um, the answer is no, by the means of 3D printing alone. You look, if there are other implants out there that have strut and node-based designs, the physics shows that strut and node-based designs behave very similar. Where 4Web really differentiates between those other strut and node-based designs is the fact that our architecture cascades throughout the entire fusion column, which is where it doesn't have a big hole through the middle of it. How do you deliver therapeutic strain through air? You can't.
Right.
So if you got a big
Yeah.
hole through the middle of your implant, you're not being therapeutic in the area that you want that effect the most, right through where the fusion is going to take place. So the 4Web technology certainly has some advantage in that area, and it's based on that structural design.
You know, one question came through here that actually is a question I had as well, and it kind of prompted because you start off with your story describing how you started the aerospace industry, and you went from the big planes down to the tiny little implants. But clearly, this kind of architecture, this kind of implant, has broader applications. So the question came in about broader applications of this implant in the orthopedic market. And Jesse, I think I might know your answer, but are you and the team, are you guys looking at future applications of this truss implant architecture in other areas of orthopedics, maybe trauma or other areas, foot and ankle, maybe, I don't know. What other
Sure.
areas do you think it's applicable?
Yeah, sure. I mean, we are. Look, the truss implant technology can be used anywhere in the skeletal system that requires structural support and can benefit from a therapeutic environment. So it is a platform that is available to treat anywhere that it is needed. And for us, it's just a matter of time and resources to be able to get this technology out to the broader market. We're very mission focused. Our mission is to positively affect the outcome of people's lives around the world through the advancement and development of the trust technology. So we are going to be there. It's just a matter of how fast we can get there. Dr. Sommer, when you think about the concept of therapeutic implants and the things that we've been talking about, I mean, are there certain areas that you can say, oh my gosh, this would be, these things being what they are, I really could see a need in this particular area, or what the implications would be on that broader market.
Yeah, sure. I mean, I could take a step back and say, Robin, you'd asked me earlier about costly biologics, and if there's a way using a therapeutic implant to sort of defray the cost by using less expensive biologics. One thing that I can say, it's off-label, but I've been doing this for a long time, is I do a lot of standalone lateral and ALIF surgeries with no posterior hardware. And it works very, very well. And I did not do that when I was using Peak or fenestrated implants that had large graft chambers. So that's something I've been doing, and we've published on for many, many years now, probably at least 10 years, if not more. We published on that. And really, the failure rate of those constructs was less than 10%, which is equal to, the failure rate of a posterior interbody fusion. So, that's one place where I've applied the technology that I didn't really have confidence in the pre-existing implants, and it's worked fantastically well, both at ALIFs and laterals. It works tremendously well. So that's one thing. I always thought this is kind of technology. It's almost like an endoskeleton. I think I've used that word with you too,
Hmm.
Jesse, where
Mm.
like this thing can really do a phenomenal recreation of the bony architecture where there may be large deficits like that distal tibia that you showed. So in my mind, that's really important. I guess I would wonder if it would behave similarly in the upper extremities that are not weight bearing, in the same way that it does in the lower extremities. But I think it can be applied anywhere in the pelvis, anywhere in the spine, and anywhere in the lower extremities without even hesitation. I mean, I use it in the neck all the time as well. So I think the sky's the limit.
Yep.
Wonderful. So, Jesse, I think in the interest of time, we should probably start wrapping up. Um, how would you like to close up with kind of an end cap uh, story to close up
Yeah.
our master class?
Yeah, no, I appreciate it. First, thank you guys both for taking the time. It's been really fun being able to talk about this. Um, I think that the possibilities are unlimited. We start looking at cost of procedures, reducing that cost of procedure. Look, we talked about those studies earlier. We are absolutely going to go, head to head with the BMPs of the world. I think. There's an interesting anecdote that I use to look at the difference of the truss technology and this chemical and induction of activity, and it's the old fable, the tortoise and the hare, right? Think about BMP as the hare. You're going to kick things off really fast, and boom, after 3 days, that hare is sitting underneath a tree with his hands behind his head, thinking he's already run the race, but it's gone. It's no longer having any impact of that healing over time. Meanwhile, that tortoise or the truss implant is just going tension compression, tension compression, tension compression. Every step that patient takes, tension compression, and will continue to go and go until that bone overtakes the implant, and ultimately the tortoise wins the race. So we are looking forward to doing a study showing that therapeutic effect gets us to where we want to go faster than something that may get off to a quick start but fades very quickly. So that is one of the things that we're doing. We're also going to be looking at high risk patients. A lot of studies that are done out there, you have these exclusion criteria, and it's not that they're cherry picking, but companies want to say, hey, here's the type of patient we want to be studying. And if it's got these other things, then it's probably going to skew our numbers, so we don't want to see it. With a therapeutic implant, we want the worst cases. We want to give those patients the best chance for success. And so I think it'd be really interesting for us to do a study in some of these other applications where we're looking at multiple revisions over time due to comorbidity or whatever the case may be. And is there a moment where we can start with the truss design that gets the job done first, fast, and a lower expense? So looking at high risk patients is going to be important. And you mentioned trauma earlier. I do have a quick thing that I want to say about that, where I think the concept of a therapeutic implant is very important. In the trauma world, well, in the normal orthopedic space, creeping substitution is used to describe the native bone eventually eating away that allograft spacer, right? And laying down new bone. Creeping substitution, the old bone's going away, the new one's going. In the trauma world, creeping substitution is actually the opposite. We're going to throw a bunch of metal in here. And when it fails, we're going to take more bone away and we're going to put more metal in. And then when that fails, we're going to take more bone away and we're going to put more metal in. So it really goes the opposite direction. And if we can redefine the treatment paradigm so that there's a classification of trauma or other types of procedures where you say, once you hit this classification, we're going truss first, not as a salvage technology. That's ultimately where we want to end up.
Jesse, if I could interrupt for a second, I hadn't thought about this before until you just started talking about the trauma cases. Like, I think one of the most difficult things to treat in orthopedics is an atrophic pseudarthrosis,
Yes.
Hmm.
hypertrophic pseudarthrosis, right? A
Yeah.
hypertrophic pseudarthrosis. We were talking about this. I was talking about this with a colleague the other day, and we're like, that's just fusion gone awry or bone growth gone awry because you're making bone. It's not mending. But when you have
Right.
an atrophic pseudarthrosis where the bone is just not there and
Mm.
not being produced, those are really, really challenging cases because how do you get the bone to be there? So if you have a therapeutic benefit, either mechanically or by cell signaling, I think
Yeah.
that's a home run. So that's a good challenge that we can look at together if you want.
It's interesting you said that. I've actually got a case study. Robin, I think this would be perfect to
Yeah.
end the session on if you guys don't
Hmm.
mind. So I
Yep.
want to pull up this case study. This one is the reason I wake up every day. Is when I watch this case study. You want to talk about motivation to know that you're out there helping people. This is the guy. This case that we've got pulled up was a 66-year-old. Had 3 years of procedures, 4 or 5 different procedures, and failed revision, had an IM nail that broke, using bone graft, really had this 8 centimeter leg length discrepancy. And I want to show you what this guy looked like. I mean, look at
Mm,
the nonverbal communication. Look at the
mm,
clothes he's
mm,
wearing. He's really hiding himself from the world. You can see the look on his face. He's struggling. He's just surviving, right? And
mm.
after 3 years plus of trying to find a solution and just, I mean, imagine the psychological toll that takes on an individual. Well, we got involved with Dr. Tetsworth in Brisbane, Australia, and he said, "Man, I got to have something for this guy. This poor guy's just he's having to deal with a lot of stuff." So he said, "Let's make him a custom implant and put this thing together." And so, we got on the surgical a call with him. He told us what the resection plans were, what he wanted. We came up with an implant that had an integrated plate, and you can see the little ridges that he was going to cable around this femur. Here you can see what that looks like here on the left-hand side, what the end result
Wow.
was, packing that. And
Mm,
look at that
mm,
fit,
mm,
right? He just kind of
mm.
slides in there, and then cabled it and put the nail back through it. And the outcome was amazing. Remember this guy that was hiding
Mm.
from the world and trying to hang on? Well, 90 days after this guy had the 4-web implant, look at that guy.
Wow. What a
Boy, that
difference.
guy, that guy's got a bolo on. He's got his beat shirt. He's ready to party. And look at the smile on this guy's face. Look at that. Look at that. That right there is why we do what we do, Rob.
Well,
And
that is that's a great way to end our outstanding discussion.
yeah,
And thank you, Jesse, so much. Thank you, Dr. Sama, so much. This was a great course, and of course, a special thank you to our audience, which this is why we do this. And thank you to our sponsor, for Web Medical. And finally, there will be a recording of this masterclass that will be available in, I think, the next couple of weeks at ryortho.com. So please do watch for that. And Jesse, I would like to invite you to say the final thank you, and we'll close our class for the evening.
yeah. Well, thank you, Robin. It's always a pleasure to speak with you and Dr. Sama. Thank you so much for taking the time to be here today. It means a lot that you for your consideration.
Yeah, thanks
Um,
for the opportunity and thanks for doing what you're doing. This really helps me help our patients. So
Yeah, and we're just happy to be where we are, and I'll just close by saying, welcome to the era of therapeutic implants.
excellent.
Perfect. Thank you, guys. Have a good night. Take
Thanks,
care.
Rob.
Right.
Thanks, Jesse.